It is one boring night. The temperature is 60 degrees Fahrenheit and it is beautiful. And I just thought I'd make a little rocket. I've been messing around with it, you know. Maybe this can be the Dan's Lab content. I don't know. Got some 91% isopropyl alcohol. I know this shit's probably in high demand, but you know, better have some fun before I die. So I'm just gonna put maybe a squirt or two in there. I've cut a nozzle hole into this cap. You can do this with one hand. Alright. So now what I'm gonna do is I'm going to cap this with my thumb. And so I've seen this demonstration before in school. You know, they take a big water jug, you know, from like a big water cooler. And so basically what they do is they take that water cooler and they fill it with ethanol, and you know, it's called a whoosh bottle or whatever. And you know, my teacher has used it many times to demonstrate combustion reactions, you know, different phases of water, things like that. So I thought I'd replicate it in more of an exciting stance. I'll give it another jet of alcohol just for good keeping. I'll give it a nice shake around to get it vaporized in there. Hopefully the stoichiometry is all right and it burns well. I try to, after each run, you have to blow a little air into it, you know, get the carbon dioxide out. All right, so here we go. Oh, shit. This is test number 2. So I've got the liquid in the rocket all shaken up, vaporized as much as I could, and we'll see how this one shoots.
You're finally awake. You were trying to cross the border, right?
But in all seriousness, wear PPE because that little jet sprayed me in the face. Anyways, welcome to Act 2 of my video. In this part, I'll explain the reaction and do some interesting math behind it. So, let's get into it. So first off, I'd like to show you the balanced chemical equation for this reaction. So 2 moles of isopropanol react with 9 moles of oxygen to form 8 moles of water, 6 moles of carbon dioxide, and it also releases energy. In order to find out the enthalpy of this reaction, we will need to use heats of formation. The heats of formation equation states that the enthalpy of the reaction is equal to the sum of the heats of the formations of the products minus the sum of the heats of the formations of the reactants. Let's begin. The molar heat of formation for water in the gaseous state is negative 241.82 kilojoules per mole. Let's multiply this by 8 and add this to the molar heat of formation for carbon dioxide in the gaseous state, which is negative 393.5 kilojoules per mole. Of course, not forgetting to multiply this by 6, taking into account the amount produced in this reaction. The product side complete, we can now move on to the reactant side. This side is easy. We subtract the heat of formation from gaseous isopropanol, which is negative 317.1 multiplied by 2 minus 0. It's easy because oxygen is a diatomic molecule, so its heat of formation will be 0 kilojoules per mole. The last step is to divide by 2 because we are not using a formation equation. We want to get the enthalpy of the combustion of 1 mole of isopropanol. After all those calculations, the enthalpy of the reaction for the combustion of 1 mole of isopropanol is negative 1,830 kilojoules per mole. Stoichiometry will prove very useful for us as we can calculate how much energy was produced by our rocket. Assuming we had 10 grams of isopropanol and it combusted stoichiometrically, we can calculate the energy produced in kilojoules. To calculate this, we must first divide the 10 grams by the molar weight of isopropanol, which is 60.1 grams. This will give us the moles of isopropanol used. We then multiply the moles of isopropanol used by negative 1,830 kilojoules. This will give us an answer of negative 304.59 kilojoules released from our rocket. We can also use stoichiometry to determine the amount of gas produced. By multiplying 10 over 60.1 by the molar ratios of water and carbon dioxide compared to isopropanol, we could determine that 0.66 moles of water will be produced alongside of 0.49 moles of carbon dioxide. Assuming that there are already 2 liters of gas in the bottle, the remainder will be expelled out the nozzle. For the simplicity of the calculation, the 2 liters of standard atmosphere will remain static and only the exhaust gases will be included in the gas law calculations. Using stoichiometry, we have determined the amount of energy produced as well as the amount of gas produced. We will now calculate the temperature of the gas produced using thermochemistry. This will then be used in the ideal gas law formula to calculate the normal and expanded volume of the exhaust gas. We will do this using Q equals mc times delta T. We first set 304.59 kilojoules equal to 11.9, the weight of the water, plus 21.6 grams, the weight of the CO2, times 2.01 plus 0.843. Now what we have done here is add up the total weight of the CO2 in the water and add up their 2 specific heat values. Now all of this is multiplied by x minus 15.56. Delta T is represented by TF minus TI. In this case, TF is represented by x because we do not know it, and we know the initial temperature to be 15.56 degrees Celsius. After calculations, TF is found to be 18.7 degrees Celsius, with delta T clocking in around 3.14 degrees Celsius. With this data roughly expressing how the gases in the bottle reacted to the energy, it can now be calculated that V equals 1.15 mole, the combined gases, times 0.082, the standard R value for ATM, times 288.7 Kelvin, divided by 1. This is the initial volume of the gas, where V equals 27.22 liters. The volume of the expanded gas is V equals 1.15 moles times 0.082 times 291.85 Kelvin divided by 1. V equals 28.81. The volume of the gas expanded 3.5% and 28.18 liters were expelled from the nozzle. Man, it sure did feel like that math was a descent into madness. I can say we're done now, and that the rocket propelled itself by its explosive force of gas. Here is a nozzle diagram explaining how it takes the low pressure gas, green, and then through the nozzle speeds it up to red. Here is a photo of the rocket mid-fire. You can see that it is bright, light white. This is because all of the isopropanol is combusting at once, causing an explosive force out the nozzle, pushing the rocket forward. Hey guys, I hope you enjoyed my first video. I'm just playing around with different styles and formatting. I'm definitely open for feedback. This time around, I'll admit the math was a little stretched thin and only theoretical. Unfortunately, dynamic formulas are just out of my math range at this time. Thus, the calculations are not 100% accurate. For this video, I've strung together everything I've learned in chemistry. Anyways, stay healthy, my 2 fans, and leave a like and subscribe. Also comment if this is a little hard to follow. I don't know about this style yet. We'll see for next video. Thanks, Dan out.